Good morning to you all. Okay, today we are going to go through the exam for October-November 2023, variant 52. Okay, so for the first question, if you can read that, two identical beakers, each of mass m, are attached to each other using string unsuspended from a pulley, as shown in figure 1.1. So this is the setup that we are given for question number one. We have two beakers. Okay, this is a beaker and that is a beaker. They have a mass, each has a mass m. Okay, and they are connected with a wire, and we have a pulley. And both are set a distance or a height h from the surface. Okay, so let us go further. The beakers are held at rest at a height h above the surface. Cooking oil of volume V is added to one of the beakers. So we are going to add cooking oil in one of the beakers with a volume V. The beakers are released so that the beaker with the oil begins to fall. This is the speed of the beaker as it reaches the surface is Z. So we are going to allow the beakers to move. Okay, this beaker is going down, that is going up. Okay, and it is falling down. It is going to gain speed. So the speed for the beaker before touching the surface is Z. Okay, it is suggested that Z is related to the volume V of the oil by the relation, and we are given this relation relating the speed of the beaker before hitting the surface as Z and the volume of the oil used as this. Okay, where A and B are constants. We have A and B are constants. Plan a laboratory experiment to test the relationship between Z and V. So if we just take a good look at the experiment, we should notice that as we add more oil and allow the the beaker to fall, it is going to have a larger velocity before hitting the surface. If we make sure always to make them fall the same distance h. So as we said before, to go about answering this question, we need to make a sketch first. This is the sketch that we, for the experimental setup that we are going to use. Okay, this is the pulley. Okay, we have two wires or a wire. We have two beakers. Identical beakers, each with a mass m. Okay, we have our surface over here. To measure the height h, we are going to use a meter ruler, perpendicular. Then we have a stopwatch. To time the to measure to measure the time uh, the beaker takes before hitting the surface. Okay. Now we make a table of all the variables, which one are the independent, which one is the dependent variable, okay, which parameter need to be calculated and which parameter need to be measured. So we are going to say that V, the volume, is the volume of oil. This is the independent variable. Why it is independent? Because it is the one that we can control. Each time we can put a known quantity or a known volume in the beaker, then we are going to measure the velocity Z. Z, velocity, dependent variable. Okay, now what else do we have? We have the mass, mass of each beaker. Okay, what else? We have H and we have H. Okay, and we have H, height of beaker above surface. Okay, so now we know all and everything. Let us start responding or answering this question. 1. Arrange the experiment setup as shown in the figure above. 2. Use a digital balance to measure the volume, the masses of each beaker, M1 and M2. And since we know that they have the same mass, or we are given that they have the same mass, so calculate the average mass as M is equal M1 plus M2 divide 2. Okay. 3. Use a meter ruler set parallel to the string or as shown in the figure. Mark a height h to always set as the height of the of both beakers as shown in the figure using a measuring cylinder at a known volume of oil to one of the beakers. 6. Allow the beakers to move freely and measure the time t it takes just before hitting the surface. Repeat the measurement twice, T1 and T2. Calculate the average time T. Take 6 sets of readings for different volumes V and their corresponding falling times T. Tabulate your findings in the table below. Calculate the velocity z as z is equal h divide t. Okay, now we have the table. We have V, it is in meter cubes. We have T in seconds. Okay, we have Z in meter per second. Okay, and what else? Now we need to go back to the original equation and see what else we should have in the table. So we have the equation saying that 2h divide z square is equal to m divide ABV plus 1 over B. Okay. So what we need to make this equation looks like an equation of a straight line that we make to make a plot of 1 over z square on y-axis and 1 over v on the x-axis. Okay, so what else do we need here in our table? uh, meter minus 6, right? Okay, and now we have 1 over, sorry, 1 over v, sorry, minus 3. Okay, and we have 1 over z square. 1 over z square, it is going to give me meter minus 2 z minus 2. Okay, these are the units. Now we say make a plot of 1 over z square y-axis and 1 over v x-axis. A straight line is expected. 11. We have the gradient. Comparing this to an equation of a straight line, remember the equation of a straight line reads as y is equal mx plus c. Okay, x stands for 1 over v. Oh, we have to divide here by 2h, right? Okay, so it is going to be 1 over z square is equal to m divide hab 1 over v plus 1 over 2hb. Now this looks exactly like an equation of a straight line. Okay, gradient is mhab. This is the gradient. Intercept, what is the intercept? This is the intercept. Okay, then therefore what we are asked for to calculate A and B. I think the thing to calculate first is to calculate B. Okay, B is equal B is equal 1 over 2h intercept. And if we know B, now we can calculate A. A is equal, from here, it is M H B times gradient. Okay, now I think we have almost there. Analysis of the data, safety and precaution to be taken. So let us say that for safety, uh, 12, make sure to carefully handle the glass beakers as not to break before hitting the surface. Maybe one more thing. It will always be difficult, to measure exactly the time for the beaker to take before hitting the surface. So maybe we can say that use a video camera system to help time to help measure the time the beaker takes before hitting the surface. I think we have almost got everything we need for answering this question. Okay. Now let us go to question number 2. A student investigates the discharge of capacitors. These are the capacitors, okay, CA and CB, in the circuit shown. The capacitors have capacitance CA and CB. The student closes the switch to charge the capacitor. So the student closes the switch over here. The capacitors start charging. As they start charging, the voltage start growing, and we can measure the voltage through the voltmeter. The switch is open and a stopwatch is started. Okay. The capacitors is the capacity discharged through the resistor of resistor R at a fixed time T. The volume reading is recorded. Okay. So you start charging the capacitors, then you see them charging over time. Then you are going to have a constant voltage. After having a constant voltage, means that the capacitors are now fully charged. You open the switch and you start your stopwatch, okay, and you watch them, the voltage, you watch the capacitors discharging, and you start watching the voltage falling for a known time t. Okay, so you allow them to discharge for a time t. Okay, for each combination, and then the experiment is repeated for uh, different value of CA and CB. Okay, for each combination of CA and CB, the combined capacitance is calculated, which is C. It is suggested that C and V are related by the relation. So we have V and C are related through this equation, where I is the initial current in the resistance. Okay, a graph plotted of ln V. So he's telling us what we should look for, ln V and 1 over C. On the x-axis, determine expression for the gradient and y-intercept. So how we should do? Okay, he's telling us that on the y-axis we need ln V. So the thing to do is to take the natural logarithm for this equation. We take it for both sides. So we have ln V is equal ln I naught R E minus T over R C R. Okay, this for both sides. Remember, ln A, uh, ln AB is equal ln A. Sorry, let me write it more carefully. Remember this, ln AB is equal ln A plus ln B. Okay, remember this. So we have over here, we have ln V is equal ln I not R, okay, plus ln E minus T over CR. Okay, is that good? Now remember that ln E to the power F is equal F ln E is equal to F. These are the properties of the ln function. Okay, they are very useful, so always remember them. Okay, the ln of E to the power F is always F itself. Okay, now we have to simplify this further. Ln V is equal, now we have this one. We are going to get the power down over here. Ln I naught R minus T over CR ln E, and this ln E we know it translates to 1. Then therefore ln V is equal minus T over CR plus ln I naught R. Okay, and he's telling us that we need ln V on the y-axis and 1 over C on the x-axis. So the gradient, if we take a close look at this one, this term, the gradient from here, it is minus T over R. Minus T over R. The y-intercept is ln I naught R. Okay? I hope this is clear for you. Okay, let us go further. Now we are told we have a table where we have CA and CB, and we have V, okay, and ln V. What we are asked to, the relation between CA and CB is so and so. We are given the relation. Okay, calculate and record values of 1 over C to the 10 to the power 4 farad minus 1 and ln V in V. Include absolute uncertainties in. Okay, let us do it one by one. Let us do it for the first column. Okay, let us get our calculator. Remember that 1 over C is CA plus CB over CA times CB. Okay. Again, let me remember. CA plus C. So CA plus CB, it is going to be 4.4 divide 2.2 square. 0.9090. Okay, we have two significant figures over here. We have two significant figures over here. So we are good to keep them to either two significant figures or three significant figures, one extra significant figure. So I'm going to keep them to three significant figures. 0.909. Okay. Let us do another one. This one, it is going to be 5.5. The addition, 2.2 plus 3.3. We divide by 2.2 times 3.3. 0.7575. It's going to 0.758. Okay, so on and so forth. So let me do the remaining. Okay. Now let us do the column for ln V. Okay, for ln V, So we need to calculate ln V. So it is ln 2.45. It is 0.896, 0.896. How we are going to decide for the decimal places and the number of significant figures? The recommendation for the lim function and the log function, keep in the lim and the log the same number of decimal places as there are number of significant figures in the original value. What does that mean? We are having here 3 significant figures. Here we are going to keep 3 decimal places, 0.896. 3 decimal places. Okay, now let us do one more. Okay, ln 2.75, it is 1.011. We are going to keep 3 decimal places. Why we are keeping 3 decimal places? Because there are 3 significant figures in the original value. Then it is going to be 1.012, 1.012, 1.012. Let me do the rest. 1.2, 120, 1.3131, 1.253, 1.348. Okay, now we need to calculate the absolute uncertainty in the ln V. So as we said before, to calculate the absolute uncertainty in a ln function, it is going to be the ln of the maximum minus ln of value. Okay, ln of the maximum and ln of the value. What is the maximum value? It is this value plus the absolute uncertainty in the value. So it is going to be ln 2.45 plus 0.05 minus ln 2.45. This is how you calculate the absolute uncertainty in the ln function. And if it is a log function, it is the same thing. It's just instead of the ln, and it is going to be the log function. So let us do the math. Ln 2.45 plus 0.05 minus ln 2.45. It is 0.02, and we keep it to 2 significant figures or 1 significant figure. This time we are going to keep it to 2 significant figures. Why we are going to do that? Because we have 3 decimal places. It's going to be 0.020. Okay. We do the same over here for this one. So it is going to be ln 2.75 plus 0.05 minus ln 2.75. 0.018. Okay, 0.018. Okay, let me do the rest with you. Ln 3.05 plus 0.05 minus ln 3.05, 0.016. Okay, ln 3.1 plus 0.05 minus ln 3.1 0.016 0.016 ln 3.5 plus 0.05 minus ln 3.5 0.014 0.014. Okay, the last one, it is ln 3.85 plus 0.05 minus ln 3.85 0.013. So always remember how we do calculate the absolute uncertainty in a lim function or a log function. If it was a log function, it would be exactly the same. Okay, you just use the log function on the calculator. Now we need to make a graph plot. Okay, let me take the values of 1 over c and 1 over v. I need to make a copy. Okay, make a paste, make it smaller, just to have them next to us so that we can see them easily while we are making the graph plot. Okay, I hope this is clear. Okay, we already got the scale. So let us see the scale, investigate the scale. It says that on this axis it is 0.1. Okay, on here it is 0.05. Okay, so each square over here it is 0.05. Each large square over here it is 0.1. Okay, this is important. So we need to plot the first value 0.909 and 0.896. 0.9 it is over here. Okay, so it is 0.91. Okay, so this is what we can do. It is 0.909, 0.91. This is the best that we can do. This 0.9. Over here, this is 0.91. And we have 0.909. Okay, almost there. Almost here. What about the V 0.89? How to calculate that? I'm going to say, then we know 0.896, it is going to be somewhere over here. How to decide that? As I have shown you before, it is 0.896 minus 0.85, and we divide by 0.05. 0.896 minus 0.85, we divide by 0.05, and we get 0.92. 0.92. Where do we look for? We are going to look for this value, this number. 9 means it is 9 squares, small squares away from 0.85. What does this value mean? It is closer to 0.9 than the 1. Okay, how we are going to do that? Let us count. Let me make it a little bit larger for you to see. Then 1, 2, 3, 4, 5, 6, 7, 8. We are 9. Okay, and it is closer to 0.9 than 1. Then it is going to be over here. Okay, now we are going to go for the error bars. What is the error bar? 0.02. 0.02. Now, how to decide the error bars? It is 0.02 divide 0.05. 0.02 divide 0.05. It is 0.4. Okay, meaning what? It is 4 small squares up and 4 small squares down. Then we start counting. 1, 2, 3. This is 4. 1, 2, 3, 4. And this is 4. What else should we do? We make a straight line like this. So this is our first data point. This is our first data point. What is the second value? 0.758. 0.758. 75.758 and 1.012. So we know it is 1.012. We know it is going to be over here. Somewhere over here. Okay, so let us do that. 0.7. This is 0.75, right? And it is going to be around here. This 0.76 around here. Okay, what about the y? It is 1.012. Then we say 1.012 minus 1 divide 0.05. How many squares are they? 1.012 minus 1 divide 0.05, 0.24, 0.24, meaning two small squares and 4. Okay, how do we decide the 4? I'm going to show you. So it is going to be 1, 2, and it is in between here and there, between 2 and 3. Closer to 2 than it is to 3. Then the data point is going to be here. So I'm taking my time to show you how exactly you can do that. So we have 0.08, the error bar, 0.018 divide 0.05. 0.018 divide 0.05. 0.36. 0.36, meaning what? It is almost 4 square up and 4 squares down. Okay, we start from here. This is 1, this is 2, this is 3, and we 0.6, then it is over here. Now we have 1, sorry, this is 1, this is 2, this is 3, and this is 0.36. It's like this. I hope you are following with me. Okay. Now what else? 0.63, 0.63. Okay, 0.63 and 1.12. 0.1. So we know it is going to be around here. Okay, 0.63 and 1.12. 6 point, what? 6.3. 6.1, 6.2, 6.3. It is almost here. Okay, and 1.1. This is 1.1, and this is 1.2. Okay, so our value is around here. This is our value. We counted it on the x, and we counted it on the y. 0.016. 0.016 divide 0.05. It is around 0.31. Let me check it. 0.016 divide 0.05, 0.32, almost there. So we count 3 squares up and 3 squares down. 1, 1, 2, 3, and it is a little bit over here. Okay, and we count down 1, 2, 3, and it is a little bit over here. Okay, now we 6.606, 0.606. Okay, 0.6, 0.606, 0.6, and we are around here. Okay, and we have 1.13, 1.13, 1.13. Okay, let us do the counting. 1.11, 1.12, 1.13, and we are up here. 0.61. We are 0.61. We are almost here. Okay. Sorry. What about our error bars? It is 0.16. It is also 3 units up and 3 units down. Almost 1, 2, 3 is over here. Count down 1, 2, over 3 over here. Okay. Now we are done here, 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 here. 0.482, 48, 48, and 1.253. 1.253. So it is around here. This is 1.4. Okay, this is 1.48, and we have 1.25, 1.25, and 3. So this is 1.255, 1.253. It is around here. It is around here. Okay. The errors bar 0.14, 0.014 divide 0.05. This is almost 3. 0.14 divide, sorry, 0.014 divide 0.05, 0.28. So 2.8 squares up. We are around here. So we are 1, 2, and we are almost here. Down, it is 1, 2, and we are almost here. Almost here. Yeah. Okay. We are again taking our time to make sure that you understand how we do everything. Okay, we have 0.357 and 1.348. 1.348 and 0.357 are going to have it over here. 1.35. 0.35. This is 0.35. This is 0.357 around here. Okay. And what we have 1.348, 1.3, 1.31, 1.32, 1.33, 1.34, 3, 4, 4, 5. It is almost here. So here's our point. It is around here. Where? Sorry. Around here. Okay. How many squares up and down? We have 0.013, 0.013 divide 0.05. 0.013 divide 0.05, 0.26. So we count 2.5, almost 2.5. This is 1, this is 2, and we have it over here. Almost. This is 1, this is 2, we have a half square, this is around here. And around here. Okay? Hope this is clear for you. Now we need to make the line of best fit and the line of worst fit. As we said, we're going to have two lines. One, the line of best fit, which we are going to use to calculate the gradient. And we are also going to draw a line of the worst fit. And this is going to help us calculate the error in the gradient and the error in the intercept. Okay. How do we do that? The line of best fit. It needs to go through most of the data or the centers of the data points. So this is how I drew it. So you use your meter ruler and try to get the line that goes through the center of all your data points as good as you can get. Okay, like this. I think this should be a good line. Okay, for the line, this is going to be the line of best fit. For the line of worst fit, we try to make sure that it can go through the edges of the error bars. Okay, to make things easy for you, maybe you can use for the worst fit the line, a dashed line. Okay, so that you can uh, decide for yourself, or it can make things easy for you. Now let us take a closer look at it. So you can see this is the line of best fit, the straight line or the continuous line, the line of the worst fit. It goes through where? If I can mark them for you, you can see I try to get him to go through the edges of the error bars. Okay, like here, and like here, like here, and like here. So we have two lines. One we consider as a line of best fit. If you can see the line of best fit, it almost go through the centers of all the data points, or as close to the centers of all data points. Okay, now we make right angle triangle to calculate the gradient. You can do something like this. Sorry. For example, then we use this triangle to calculate the gradient for uh, the lines. You can use one triangle, or you can use two different triangles for each line, as you wish, or as you prefer. Okay, I usually typically use one triangle that I can use to calculate both uh, both lines. Okay, so what do I get? Is what I get for the best fit line. Best, sorry, best fit. This is the gradient, 1.315 minus 0.9, 0.4 minus 0.89. I get minus 0.847, and I remember the multiplication 10 to the power minus 4 farads. The worst fit line, I get a slope of 1.33 minus 0.9 divided by 0.4 minus 0.88. What do I get? 0.896 times 10 to the power minus 4 farad. Okay, so this is the best fit. I'm going to report it, including the absolute uncertainty. How to calculate the absolute uncertainty? It is the difference between the best fit and the worst fit. There's going to be 0.847 minus 0.896, and I don't care for the uh, for the sign. Is it positive or negative? It doesn't make a difference. So it is 0.85, and the difference is 0.05 to one significant figure. So it is 0.05. How many decimal places? We have two. So the value for the best fit, I'm going to quote it to two decimal places. I just make them smaller. Sorry, 0.4 minus 0.88. Okay, so this is our gradient, and we have the units. Sorry, let me write it. Minus 0.85 plus or minus 0.05 times 10 to the power minus 4, and we have farad. So we are done calculating the gradient. Okay, now the next question is determine the y-intercept of the line of best fit. Do not include the absolute uncertainty. So how to do that? We are going to take a point on the graph. Let us say I will pick this point. Okay, this point got 0.42. Okay, or 41, and times 10 to the power minus 4, and the y-axis is 1.30. Okay, so this is the point I'm going to use. 0.41 times 10 to the power minus 4 and 1.30. Okay, now we have y is equal mx plus c. C is equal y minus mx. What is y? It is 1.30. What is m? It is a gradient, right? 0.85 times 10 to the power minus 4 plus minus and a minus 0.85 times 10 to the power 4. Okay, minus 4 times x 0.41 times 10 to the power plus 4. Then we have 1.30 plus 0.85 times 0.41. Okay, let us have our calculator. So we have our calculator and we do the math. So it is 1.30 plus 0.85 times 0.41. 1.648 1.649. Okay, does it have units? It is the y-intercept, okay, and got the unit of the y-axis, okay, so it doesn't have units over here. Using your answers to A, C, so and so determines the value of R and I include appropriate units, and we are given T is equal 30 seconds. So let us see how T, R and I not related to anything. So we remember that the gradient is minus T over R and the intercept is ln I naught R. Okay. So we have the gradient is equal minus T over R. Therefore, R is equal minus T divide gradient. We substitute that. We know we are given T is 30. Okay, we divide by 0.85 and 10 to the power minus 4. Okay, we do the math and we get 3.53 times 10 to the power 5 ohms. 3.53 times 10 to the power 5 ohms. Okay, now we know that the intercept is equal ln I naught R. Okay, therefore e to the power intercept is equal I naught R. Therefore I naught is equal e to the power intercept divide R, which is going to be e, and we know the intercept is 1.649. Okay, and we are dividing by R, which is 3.53 times 10 to the power 5. Okay, let us get our calculator. So it is a E 1.649. Okay, and we divide by 3.53. We get 1.47 10 to the power minus 5. 1.474 times 10 to the power minus 5. Okay, 1.47 10 to the power minus 5, and we remember the units for I, which I think it is current, or I know it is current, then it is in amps. Okay, sorry. Now we are being asked to determine the percentage uncertainty in R. So what is R? R is equal minus T divide gradient. Okay, then we know that delta R over R is equal delta T divide T plus delta gradient divide gradient. This we know if we have a function which is A times B. We know that delta F divide F, percentage uncertainty of the quantity, is delta A divide A plus delta B divide B. Okay, so we have delta T divide T. For delta T, we have 1 second, and T is 30. So we have 1 over 30. For the gradient, we already know that it is 0.05, 0.05 divide 0.85. Okay, then we multiply by 100 since we are asking for the percentage uncertainty. So let us do the math. 1/30 plus 0.05 divide 0.85 times 100. It is 9.21. 9.2%. So this is the absolute or percentage uncertainty in the measurement of R. Now, the last question. The experiment is repeated, okay, with the same value of t, meaning that it is t is equal to 30 seconds. Determine the combined capacitance C that gives a value of Y of V of 1.2 volts. Okay, let us remember this equation. This one. So this equation is basically ln V is equal minus T over CR. So he's asking for 1 over C. So it is gradient divide C plus intercept. Okay, so we remember this equation. We have ln V is equal gradient divide C plus intercept. Let us rewrite this equation. So ln V minus intercept divide gradient is equal 1 over C. Therefore, C is equal gradient divide ln V minus intercept. Let us substitute for that. So the gradient is 0.85 times 10 to the power minus 4. Ln V, it is ln, we are given V is 1.20 minus the intercept. What is the intercept? 1.649. 1.649. Okay, so let us do the mass. We have 0.85 divide, we have ln 1.2, okay, minus 1.649. Oh, we have a minus here. The gradient got a minus sign. Okay. So how is it? How much was it? 0.579. 0.579 times 10 to the power minus 4. Sorry. Farads. Okay. It is 0.59 times 10 to the power minus 4 farads. And this concludes this paper. Okay. It wasn't a difficult one. It was an easy going paper. Okay. Good luck. And I hope this video was useful for you. Cheers.